take a look at today's lesson. So we're going to be looking at combining functions in a couple of different ways. This mostly review. I don't think this is really anything very new, but let's go ahead and take a look at it. So we're going to look at combining functions in this way, where we're adding them, subtracting them, multiplying and dividing them. And the way that we would find their domains would be the intersection. So we would find the domain of f, and then we would find the domain of g, and we would intersect those domains. Do we remember what an intersection is versus the union of domains? Do we remember intersection? Intersection is you just choose the elements that are common, right, that are common in both domains. That would be the intersection. So we're going to take the intersection of those two domains. So that's how we would combine functions, by adding, subtracting, multiplying, or dividing. We're also going to look at composite functions. So composite functions, we've got a picture of that right here. Two different kinds of notations. They mean the same thing. I actually prefer this kind of notation. I think that's more telling about what to do. That means that you take the function g of x and insert it inside of f of x everywhere there's an x, right? You probably remember that from last year. Means the same thing. It means f of g of x. We just need to be comfortable with both kinds of notation, since we'll probably be facing both kinds. Even though we may have a preference, we just need to understand what that means. So we'll also deal with composite functions. All right, and the other thing that we're going to look, it's certainly possible to add functions graphically. Basically, you have the graph of each function and you create the graph of the addition of them. What this is talking about, the graph of the addition or subtraction of two functions, or multiplication or division, really any of those operations. You can add them graphically. Basically, the way that you do that is you add their corresponding, oh, and that's kind of left the page, sorry about that, their corresponding y coordinates. Okay, so that's what we're going to be doing. Let's look at some examples of all of that. I just have a couple of them. There we go. Okay. So the first example, we're given two functions. We're given f and g. We want to do two things. We want to add them, and we want to divide them. That's just what this particular example is asking us to do. So let's do that. Okay, so we would do f plus g. It's going to be equal to 1 over x minus 2 plus the square root of x. Now, since those are two different kinds of functions, one is a rational function and one is a radical, right? The rational is the fraction and the radical has got the square root. We can leave it like that. That's okay. If we wanted to find a common denominator, we could, which would be just fine. So we would multiply this one by x minus 2 like that. And then that would give us 1 plus the square root of x times x minus 2 over x minus 2. So let's look at the comparison. So I could have written either 1 over x minus 2 plus square root of x. That's an option. Or this one. You see why in this particular case they both are acceptable? Because when we add them together, does that make it any smaller? When we're simplifying, we're looking at making it compact, right? Shrinking it down. When I add them together, it's, I don't know, it's about the same, right? So either one of those would be fine. Okay, so that would be the answer for adding them together. Now we need to look at their domains. So we need to think back to what that requirement was to find the domain of f and find the domain of g and then intersect those domains. So let's look at that. The domain of f is basically includes everything except a 2, right? 2 would make that undefined. Any other x would be fine. So that domain would be negative infinity to 2 and 2 to infinity. Okay, that's the domain of f. The domain of g, what works in the square root of x? Just 0 to infinity. Can we include 0 or not? Can we in this case? We can in this case because it's not in the denominator, right? It's the square root of 0 is 0. So this little guy's domain is from 0 to infinity. Now the domain of our addition of those two functions has to be the intersection of those two domains, the intersection. So that means I can only use the elements that are common. So I can go, let's see, I can pick up the 0 to 2, right? That's okay, including the 0, because 0 is okay in both of them. So let's do our domain. So the domain of this little guy, we're going to pick up the 0. Can I include the 2? No, I can't. Okay, and then I would go, what? And then I could include the other side, so 2 to infinity. So here's our domain, and there's our functions for the addition. We okay with that? Okay. Let's look at the division of those two. So we're going to divide f divided by g. And so that would be 1 over x minus 2 divided by the square root of x. Now hopefully we understand that leaving complex fractions is never okay, right? We can't do that. So let's think about this as being over 1, and let's flip and fix our complex fraction. So f over g should look like 1 over x minus 2 times the square root of x. Okay. So we still have, we've got to do the intersection of those two, of f and g, which we pretty much have in that top one. But is there an additional problem with this? There is, isn't there? In this particular one, I can't include 0. Right? I can't include 0 because that would cause the denominator to go to 0, or the square root of 0 is 0, so that would be a problem. So we have a little bit of an adjustment on this one. We just need to pay attention. So instead of including 0, I just don't include it, and then the rest is the same, because we already did the intersection of those domains. So there's our division of f and g and the domain of that. We okay with that? Good? See, this is right. This is fine, right? Yes, they can get a little complex, but that's the main idea. All right, we have one other example. Let's do that one. So this is where we're going to do composites. Now, composites are a little different when they're domains, and it gets really confusing. So probably the most confusing thing about these two is the domains. That's probably the most historically for students, the most confusing thing is the domains. So in the first piece, for the addition, subtraction, multiplication, and division of functions, it's the intersection of the two domains, period. Okay? If there's a division, there could be an extra restriction. But other than that, it's the intersection. So we just need to keep that straight in our heads. It's the intersection of the two. For composite functions, we are actually building a new function. And so we're building a new function. It's going to be the combination of one inserted into the other. So the domain is a little bit different. Let's go ahead and jump in and let's find the composites, and I'll talk about the domain as we work through them. So we're told that f is the square root of x and g is the square root of 2 minus x. Okay, great. So the first thing they want us to do, correct, so I don't like that, basically g of f of x. Okay, that's clear. That means I'm going to insert f of x inside of g of x. Okay, so let's do that. So I've got the square root of x, that's f of x, so I'm going to insert in place of this x, I'm going to put 2 minus, where are we? Oh, we're going g, f into g, so we're doing the opposite. So we're right here. Okay, so I'm going to take this one and I'm going to put it right in there. We're inserting f into g, so it goes right where the x is. Okay, so that's g of f of x. Okay, all right. So it's domain. The domain is not going to be the intersection of the two functions. So I need to find the domain of this new creation, right? This new creation. So we know with radicals, like we learned in the other one, they can't be negative underneath there, right? That causes imaginary numbers. So what I have to do to basically, be safe against that is I need to take the inside, 2 minus the square root of x. I need to force that to be greater than, is it allowed to equal 0 in this case? Yes, greater than or equal to 0. That's what I need to have happen. I need that to be greater than or equal to 0. Okay, so let's solve that. So I'm going to move the square root of x over. I added it to both sides. So we can think, it's kind of weird with a radical, we can think about squaring both sides. So basically I've got x is less than or equal to 4. Okay, so that works. X is less than or equal to 4 works for this piece of it. But what about the big piece? So if let's say x is x is less than or equal to 4. Let's say x is a negative number. Let's say this piece right here. Let's look at this piece. It says x has to be less than or equal to 4. What if x was negative 2? Is that okay? No, that's not okay because of this little piece right here. This piece we have fixed, right? We have safeguarded this by what we did right here. Underneath this big radical, the one that's over that, we know that's going to be okay. But we also have this other radical right under here that we have to deal with as well. So this radical right here, x has to be what? Greater than or equal to 0, right? Could it equal 0 in there? It could, right? Because 2 minus 0 is 0. So I've got to combine these two together for my final domain. You see why domain usually drives students crazy? They're like, oh my gosh, what are you doing? Domain is usually the issue here. So let's see. We want x to be smaller than or equal to 4, but we want it to be bigger than 0. So the intersection of these two, we can write it in various different ways. We can write it as x has to be, what? X has to be bigger than 0 and smaller than 4. We can write it in, let's just write it in this form. So it could be 0, has to be bigger than 0, and it has to be smaller than 4. Is that okay? So it's bigger than 0 and smaller than 4. That's just an interval notation to do it. Okay? So that's way different than the original ones, right? That's way different than the intersections of the domains of f and g. It's completely different. That's really, really small. It doesn't exist for just a really, really small interval. All right, our second one. So for some students, like f of x, they're like, what? That's the same function. You're basically substituting the same function inside of itself. That just seems really weird. But that's what we're doing. So f is the square root of x, and f is the square root of x. So that's what our function looks like, the square root of the square root of x. Which with radicals, that's just very strange. I think it would make more sense to us if we put it in exponential form and then back into radical form if we wanted to. So what do we have going on? The underneath, that's x to the 1/2. And then that's raised to the, the outside one is, the 1/2 power. So if we clean this up, we would get x to the, and I'm sure we remember our exponent rules, power to power is multiplying, x to the 1/4, and to put it back into radical form, it would be the 4th root of x. That's what our f of x would look like, the 4th root of x. So do we have any issues with the 4th root? Can we put any number in there that we want? We cannot. Okay, it's similar to square roots. Okay, it's similar to square roots in that if it's an even root, it can't have a negative number in there. Even roots are not allowed to have. What about if it's an odd root? Is that okay? Yeah, negative numbers are fine with odd roots, but not with even roots. So for this one, our domain is going to be what? What's our domain going to be? 0 to infinity. Very good. 0 to infinity. And I'm including 0. Okay, how is that? We okay?